Hello friends, welcome to this lecture. In previous lecture we have discussed some basic concept of ordinary differential equation, and we will continue our discussion in this lecture also. And in this lecture we basically want to discuss the existence and uniqueness theorem for ordinary differential equation. So let us discuss the following. So it means, what is the problem? That consider the differential equation dy by dt equal to f t y, where with the initial condition y t naught equal to y naught, and here f is a given function of t and y. Our aim is to find a solution of the given differential equation, that is to construct. It means what? It means we need to find out a suitable function y which satisfy the differential equation dy by dt equal to f t y in a neighborhood of t naught, and the graph of f contain the point t naught and y naught. So we have discussed certain problem of this dy by dt equal to f t y and y t naught equal to y naught. Let us discuss some more problem, and with the help of these examples we try to discuss more theories. So if you look at this example 1, here we have the linear differential equation. So consider the following differential equation: y dash plus y by t equal to 2, and here t is greater than 0, and the initial condition along with this differential equation is y1 equal to 2, and we can easily check that a solution of 2 is given by yt equal to t plus 1 by t. In fact, if you look at this is a linear differential equation, y dash plus y by t equal to 2, and you can find out the integrating factor here. And if you use integrating factor, I think it is integrating factor is e to the power minus pt dt. So if you can calculate this, then it is coming out to be, and pt is what? The coefficient of y, that is 1 by t. So it is going to be what? It is e to the power minus integration of 1 by t dt. So it is e to the power minus ln t. So it is giving as 1, sorry, it is not minus, it is plus here. Integrating factor is this, so it is coming out to be t here. So integrating factor is t here, so you just multiply by t here, so it is coming out to be y dash t plus y equal to 2t. And if you simplify this, the first term is what? D by dt of ty equal to 2t. And if you simplify, this is what? You can simply say that it is ty equal to t square plus c. So you can say that y is coming out to be t plus c by t. Now this c is a constant which you can find out using the initial condition y1 equal to 2, and you can say that when you put y1 equal to 2, your c is coming out to be 1. So your solution of this problem 2 along with the initial condition 3 is given as yt equal to t plus 1 by 2, and we have already seen that the general solution of this initial value problem is given by t plus c by t. And we can observe that what we want to observe here is that the solution yt equal to t plus 1 by t is having problem when we take t is tending to 0. What do you mean by problem? That here the solution is tending to infinity as t tending to 0, and that we can say that since the equation has a singularity at t equal to 0, here if you look at the coefficient of y is 1 by t, and is t tending to 0, then y by 1 by t is tending to infinity. So it means that this differential equation itself has a say singularity at t equal to 0. So we may consider that of course solution may also have the similar kind of nature. It means that solution will also tend to infinity as t tending to 0. So that is the observation we can observe from this. But if you look at the same differential equation, but with a new initial condition, that is y1 equal to 1. In a previous we have condition y1 equal to 2, but now we are considering the same differential equation with y1 equal to 1. So if you look at the general solution is given as yt equal to t plus c by t. Now if you put the condition that y1 equal to 1 in place of 2, then we can say that c is coming out to be 0. So it means that here the solution is given by yt equal to t. But this create a little bit problem. Why? Because if you look at the differential equation, this differential equation has a problem at t is equal to 0, means as t tending to 0, the coefficient function of y is going to be unbounded as t tending to 0. But if you look at the solution here, that solution yt equal to t is very nice, and we can say that the solution behave very nicely at the point t equal to 0. So at this point we may say that in case of linear differential equation, that is dy by dt plus at yt equal to bt along with the initial condition yt not equal to y naught, the solution may not be necessarily discontinuous at the point where the coefficients are discontinuous. So it means that if at is discontinuous at a particular point, say t equal to t naught, then solution may not be discontinuous at that particular point. But if a solution is not continuous at some point, it is only those points where coefficients are not continuous. So it means that it may not necessary that solution may have discontinuity at the point where this at is discontinuous. But if at all solution has a discontinuity, it has to be along the point where at is discontinuous. That is the observation we have observed from the previous this current example. Now we want to consider one more example, but this time in place of linear differential equation, now we want to consider the non-linear initial value problem. And we can say that if we consider a non-linear initial value problem, then situation may be quite different. In general, there is no relation between the region where the function f t y is continuous and the region where the solution exists, right. So initially in case of linear differential equation, we have seen that solution may not be discontinuous at all, but if it has a discontinuity, it has to be only at those points where the coefficient functions is having discontinuity. But in case of non-linear initial value problem, this is quite different. Here we may see that there is no relation between the region where the function f t y is continuous and the region where the solution exists. For example, consider the following non-linear differential equation: y dash equal to y square with the condition y 0 equal to y naught. Here y naught we are considering as a positive real number. Now the general solution of 5, this equation number 5 is given by yt equal to minus 1 upon t plus c. This you can easily calculate. It is a separable equation, and you can solve this separable equation along with this initial condition. So you can find out the value of c using the initial condition y 0 equal to y naught, and if you apply that initial condition, we can say that the solution is given by yt equal to y naught divided by 1 minus y naught t. And here we can see that the function this y dash equal to y square, the nonlinear function y square is continuous for all t belonging to R. So here this is a continuous function for all t, but the solution is going to be unbounded at t equal to 1 by y naught. If you look at here, since y naught is positive, so 1 minus y naught t is going to be 0 at t is equal to 1 upon y naught. So it means that the solution is going to be unbounded when t is equal to 1 by y naught. So it means that the solution is valid only in the interval minus infinity to 1 by y naught. So what and also so here we have seen that the solution may not have any relation that where f t y is continuous, and solution may not be continuous in that kind of interval. And also we have seen that there are some initial value problem which have one solution, more than one solution, and no solution at all. This we have seen in previous lecture. So if you consider all these two examples along with the initial value problem which we have discussed in previous lectures, we may ask the following questions. First, that how do we know that the initial value problem has one or more than one solution? First of all, we are not sure whether a given initial value problem may have a solution or not. But if we have a solution of one, then whether it is unique or not. It means our second question may be like this, that if we have a solution of one, then we need to worry about the uniqueness of the solution. It means that it may happen that the same initial value problem may have 2, 3 or infinitely many solution of one. So, this is our second doubt. Third doubt is why we are worrying about the existence of solution. After all, what is the use of determining whether one has a unique solution if we are not able to find it explicitly? It means that it may happen that a given initial value problem has a solution. It means that we are able to find out the solution of the first two problem, that it has a solution, it may have one solution or more than one solution, but we are not able to find out the solution in a explicit manner. It may happen that the existence is proved, but we are not able to find out the solution in explicit manner. But this question 3 may not have much problem, because nowadays we have several software, very important, very useful softwares are available, which can find out the solution not in analytical manner, but they can find out the solution in a numerical manner. It means that you can always find out a solution which is accurate up to 3-4 decimal place or whatever desired accuracy we want. We have very good software. So, I think this third question may be solved if we have a software and we can find out the solution which is accurate up to decimals few places, maybe 4 places, 8 places or 16 places. So, here in this lecture and coming lecture, we want to discuss the condition by which we can solve these 3 questions. So, once we know that, we want to understand the importance of the first 2 problem, that once we know that the differential equation 1 has a unique solution yt, then we have a license to find out a analytical or numerical solution of the one. So, it means that first thing we want to consider that a given differential equation has a solution or not. If it has a solution, we need to worry whether it has a unique solution or not. If it is if that differential if the initial value problem has a unique solution, then we try to find out the method to find out that particular solution. And it is very advantageous situation when we have a unique solution. So, how to find out that unique solution? What we try to do here, we try to approximate the solution of the initial value problem using different iteration schemes. So, here we want to find out one iteration scheme which is known as Picard iteration scheme, and what we are going to do is the following, that we have the following algorithm for proving the existence of a solution yt of 1. Construct a sequence of function y and t which come closer and closer to solution of 1. It means that somehow we want to find out a sequence of function which is going to be converged to the solution of the problem 1. So, first we need to construct a sequence, and then we want to find out that this constructed sequence has a limit yt in some kind of interval, say t0 to t0 plus alpha. That alpha we need to find out in this particular procedure. And third, very important thing, that we need to show that this limit which we have considered as a limit of the sequence, this limit is a solution of 1 in the said interval. That is the say outline of the following theorem which we are going to discuss. So, first thing is construct a sequence, second is that we need to show that this sequence has a limit in some interval, and third is that limit is actually a solution in that particular interval that we are going to see in this lecture. So, to consider the existing theorem, first let us assume that suppose f is continuous in a domain D and that t0 y0 is an arbitrary point of D. So, first step towards the existence result is to show that the initial value problem dy by dt equal to f dy with the condition yt0 equal to y0 is equivalent to the following integral equation yt equal to y0 plus t0 to t fs ys ds, where t is belonging to some interval. And to show the equivalence between this differential equation and the integral equation, we consider the following lemma. We says that a function yt is a solution of initial value problem dy by dt equal to f dy with yt not equal to y naught on an interval I if and only if yt is a solution of the integral equation 6 on the interval I. So, first we need to show the equivalence, and then we proceed with the existence theorem while showing the solution of this integral equation. So, let us prove the existence so equivalence of these two differential equation and integral equation. So, if y is a solution of dy by dt equal to f dy on I satisfying yt not equal to y naught, we have y dash equal to f t yt. Here y dash denote the symbol dy by dt, and we integrate from t naught to t on this, and we have what yt minus yt naught equal to t naught to t fs ys ds when t belonging to I. Now, here we already have this condition that yt naught equal to y naught. So, it means that this I can write as yt equal to, so this we can write as yt equal to y naught plus this integral t naught to t f of s comma ys ds, and which is nothing but equation number 6. So, it means that we have shown that if y is a solution of this differential equation initial value problem, then y is a solution of this integral equation. Now, we want to show the converse part. Conversely, if yt is a continuous solution of 6, then by the continuity of the function f t y t, the right hand side means this side is differentiable. So, differentiable, then by the fundamental theorem of calculus we can verify that yt satisfy the differential equation. So, we simply differentiate this, and when we differentiate this, this will give you y dash t, this is a constant. So, this will be 0. So, y dash t equal to, and this we derivative of this using Leibniz theorem, we can consider that it is nothing but y dash t equal to f t y t. And if you look at this integral equation, and if you put t equal to t naught, then we will get yt naught equal to y naught, because this term is going to be 0. So, it means that from the integral equation we can say that yt naught equal to y naught and y dash equal to f t y t. So, it means that we have seen the equivalence of the initial value problem and this integral equation. So, once we have equivalence, we want to find out, we want to discuss the existence theorem. So, with the help of this lemma, we will establish the existence of a solution of 1 by proving the existence of a solution of 6. So, so it means that our working procedure is to find out the solution of the integral equation rather than solution of the differential equation. Now, these two are equivalent, so we can show that once we have the existence solution of integral equation, then we have a solution of differential equation. So, now our problem is to reduced to find a solution of the associated integral equation. That is our problem now, and that is now we want to find out a function such that it satisfies 6. Now, here it may happen that we can integrate right hand side, that is f t y t is some function of t which we can integrate, or you can simply say that if this part, if you look at this, if this is integrable f s, we can find out this integral in a precise manner, then we can find out this solution y t in a precise manner, in explicit manner. But problem occurs when we do not have a function like this which can be integrable. So, it means that therefore, next we try to approximate the solution of integral equation, because we are not able to find out the solution in an explicit form. So, let us start with the initial condition y naught as our first guess. So, once we want to find out the approximate solution, the first guess is the condition this y t naught equal to y naught, because we already know that at point t equal to t naught it satisfies the initial value problem. So, our first approximate is the this y t is y naught. So, here if you look at what is our problem here, if you consider this, we have this problem y dash equal to f t y t, and here y t naught equal to y naught. So, we have seen that it is equivalent to the following integral equation, that is this T naught to T f of s y of s d of s. So, that we have already seen. Now, it all depend on this integral. If this is if we are able to find out this integral in a explicit manner, we have a solution, but if it is not we are not able to find out this integral, then we are in trouble, that we are not having a solution. So, what we try to show that if we try to approximate the solution in the following manner, we suppose we say that here we say that if we replace T naught to T f of s, now in place of y s, if we say that, let us say that this y naught s is an approximation of the solution y s. So, we want to find out the approximation of y t. So, first guess is, let us say that in place of y, if we put y naught s. So, just calculate this and we call this as y 1 t, and it is we call this as a first approximation. So, calculate this quantity y naught plus T naught to T f s y naught s d s. Now, if we calculate this quantity and if we say that y 1 t is coming out to be y naught, this implies that y naught is equal to y naught plus T naught to T f of s y naught s ds. Here this y naught s is nothing but y naught. So, it means that what we have shown here, that this y naught satisfy, if y 1 t is y naught, it means that y naught satisfy this integral equation. This implies that your y t is nothing but y naught, and y naught is a solution if it happened. But if it not happen, it means if y 1 t is not y naught, then we have to move further. So, that we are going to discuss here. So, here we say that the first approximation is given as this y 1 t equal to y naught plus T naught to T f s y naught d s, where t belongs to I. And if y 1 t is y naught, then we have shown that y t is equal to y naught is indeed a solution. If not, then we try y 1 t as our next guess. So, by taking this y 1 t, we define y 2 t as y naught plus T naught to T f of s y 1 s t of s, and then we try to see that if y 2 t is coming out to be y 1 t, we stop and we say that y 1 t is our solution. If we say that y 2 t is not y naught, then we move to next guess, and in this way we can define a sequence of approximation solution y 1 t, y 2 t, y n t as follows. Here y t naught is equal to y naught and y j plus 1 t equal to y naught plus T naught to T f s y j s d s, where j is from 0, 1, 2, 3 and so on, and these function y and t are called successive approximation or Picard iteration. And we once we, so the first process is done, means we are able to find out the we are able to construct the sequence which we trying to prove that this sequence will converge to the solution of the integral equation. So, as pointed out in a previous example, that the solution of nonlinear differential equation may not exist for all time t. Therefore, we cannot expect the Picard iteration y and t of 1 to converge for all t, because we have already seen this example. If you remember this example, that y dash t equal to y square, right, and we have seen that the solution exists only for this interval minus infinity to minus 1 upon y naught. Here y naught is positive and y t naught is defined as y naught. In fact, here t naught is equal to 0. So, we have seen that in this particular example, we have seen that solution may not exist for all time t. So, it means that whatever we are going to prove, we will prove that it will not converge for all time t. So, it means that to provide us with a clue of where the Picard iterates converge, we try to find out an interval in which all the y and t's are uniformly bounded. It means that we need to find out the interval such that your y and t is bounded by some, say, constant k, where k is some fixed constant k. So, now we need to find the interval in which y and t of the previous equation convergent. In other words, we want to find out a rectangle in which the graph of yn will be contained. So, we need to find out the interval in which y and t convergent. In other words, we want to find out a rectangle in which the graph of yn will be contained. So, that we are going to do, and that is very much related to the nonlinear function f. So, let us first assume that f and del f by del y are continuous function on a closed rectangle, where rectangle R is defined like this. It is set of all t and y, where t is lying in this interval t naught to t naught plus a, and y minus y naught is less than or equal to b, where a and b are some real constant, and this is a rectangle is centered at t naught and y naught. And it means that the function f, which we have assumed as a continuous function, and del f by del y, which we also assume that it is continuous function, is though this function f and del f by del y are bounded above by constants m greater than 0. So, we have assumed that there exists a constant m such that modulus of f t y is less than or equal to m, where t y belongs to this R, and del f by del y is also bounded by another constant k for t and y belonging to this rectangle R. So, we say that if del f by del y is continuous in R, then there exists a positive constant k such that modulus of f t y 2 minus f t y 1 is less than or equal to k y 2 minus y 1, where t y 1 and t y 2 belongs to R for all points t 1 y 1 and t 2 y 2, t y 1 and t y 2 belongs to R in R. So, that we show that del f by del y is continuous in R is equivalent to the condition this, and this condition has a name, very important name, that we are going to discuss in next slide. So, first let us prove this lemma. So, here we say that if t y 1 and t y 2 are 2 points in R, and assume that this y 1 is less than y 2, then by Rolle's mean value theorem we can say that there exists a number eta between y 1 and y 2 such that f t y 2 minus f t y 1 is equal to del f by del y t comma eta y 2 minus y 1. And we can say that since the point t and comma eta is also in R, then we can say that del f by del y at this point t and eta is bounded by this k, that we have already assumed here in this thing. Here we assume that modulus of del f by del y is less than or equal to k. So, it is true for all t y in this rectangle R. So, in particular it is also true for this t and eta. So, del f by del y at the point t eta is also bounded by k. So, here from this we can say that modulus of f t y 2 minus f t y 1 is less than or equal to k y 2 minus y 1, and it is valid whenever t y 1 and t y 2 are in R, are in this rectangle. And this condition has a name, and we define we try to give this inequality as a following thing: a function f that satisfy an inequality of the form 12 for all t y 1 comma t y 2 in the region R is said to satisfy a ellipsis condition in R, and k is called the ellipsis constant. So, it means that if f satisfy the condition given in 12, then we say that f is f satisfy the ellipsis condition, and the condition the constant appearing here is called the ellipsis constant. So, the above argument shows that if f and del f by del y are continuous on R, then f satisfy a ellipsis condition in R, but converse may not be true. In fact, there are some function f which satisfy the ellipsis condition in a region, but do not have a continuous partial derivative with respect to y there. For example, if you consider this function f t y equal to t modulus of y, and you define in a region containing the point 0 0. So, in our existence result we need to assume that f satisfy a ellipsis condition in y, and not the strong assumption about the continuity of del f by del y. So, we are discussing this ellipsis condition because in existence and uniqueness theorem we are going to assume that f satisfy a ellipsis condition. that is why we are discussing the ellipsis condition. So, here we can simply say that since f is not the partial derivative of f does not exist, we simply say that derivative by dy is not continuous in a region where 0 0 is contained. But we can easily see that this satisfies the ellipsis condition. You can see like this. Here we can simply say that f t y is equal to t modulus of y. So, here we can say that f t y 1 minus f t y 2, it is t modulus of y 1 minus t modulus of y 2 is equal to modulus of t y 1 y 2 minus y 1, and we already know that it is what it is, and here we can say modulus of y 2 minus y 1. Now, this t belongs to some interval. So, we can say that if it t belongs to t naught to t naught plus h, we can say that t is bounded by h. So, we can write h y 2 minus y 1. So, we can say that f satisfies the ellipsis condition like this. So, since t belongs to t naught plus h, we can say that this t is bounded by t naught plus h. So, here you can say that f is satisfying the ellipsis condition like this, but we have already seen that since it has no partial derivative, we say that though f is satisfying the ellipsis condition, but here partial derivative is not continuous. We can say that this existence, that partial continuity of partial derivative is a stronger condition than the ellipsis condition. Now, we consider one more example where we say that if f t y is equal to y to power 1 by 3 in a rectangle R, which is defined like this, is a set of all t y such that modulus of t is less than or equal to 1, modulus of y is less than or equal to 2, then we can say that f does not satisfy ellipsis condition in R. To establish this, we need only to produce a suitable pair of points for which this equation number inequality 12 fails. So, here we the purpose of this example is that it may happen a given function may not satisfy the ellipsis condition in some region, some rectangle, but it may satisfy the ellipsis condition in some other rectangle. So, to show that first of all that it does not satisfy the ellipsis condition in this rectangle, we need to show that this condition is not true, the condition this f t y 1 minus f t y 2 less than or equal to k times y 1 minus y 2. So, this will not hold for any constant k. So, to show that, let us consider 2 points, say t y 1 and t comma 0, where t is lying between minus 1 to 1 and y 1 is some constant which is bigger than 0. And if you look at this quantity f t y 1 minus f t y 0 divided by y 1 minus 0, here y 0 is simply 0. So, f t y 1 is nothing but y 1 to power 1 by 3, and f t y 0 is simply 0 and divided by y 1. So, we can have this as y 1 to power minus 2 by 3. So, this to show that such a k does not exist means we have to show that the f t y 1 minus f t y 2 divided by y 1 minus y 2, we can say that this condition is equivalent to this condition. So, if we can show that this is an unbounded thing, then such a k does not exist. So, that is what we are going to see it here. So, we can say that choosing y 1 greater than 0 sufficiently small. So, here this we can choose this y 1 sufficiently small, and we can show that this y to power minus 2 by 3 can be made larger than any preassigned constant. So, it means that this quantity y 1 to power minus 2 by 3 can be made unbounded. So, it means that there exists no k such that modulus of y 1 to power minus 2 by 3 is bounded by any constant k. So, it means that you if you produce any constant, we can take y1 small enough such that it is going to be bigger than that constant. So, it means that what we have seen here, that this f t y which is given as y to power 1 by 3 is not satisfying the ellipsis condition in the rectangle this. But we can also see that first of all what we have seen is this, that there exists some function f t y t and a region R where f does not satisfy the ellipsis condition. The nonlinear function f t y equal to y to power 1 by 3 may satisfy the ellipsis condition in some other rectangle. For example, if we define a rectangle like this, R1 equal to set of all t y such that modulus t is less than or equal to 1 and modulus of y minus 2 is less than 1. Look at here, the quantity y1 to power minus 2 by 3 is going to be bounded by some constant k. So, here we have seen that in one rectangle it does not satisfy the ellipsis condition, but in some other rectangle it may satisfy the ellipsis condition. So, it means that we are going to use in coming existence and uniqueness theorem. So, here we have seen that this function f t y equal to y to power 1 by 3 is not satisfying the ellipsis condition in rectangle R, which we have defined as this. Here we have seen that this nonlinear function f t y equal to y to power 1 by 3 does not satisfy the ellipsis condition in this rectangle R, but we have seen that this function may satisfy the ellipsis condition in some other rectangle, for example in this rectangle, and here we can say that here this quantity y1 to power minus 2 by 3 is actually bounded by some constant k. We can always find out the constant k such that del f by del y is bounded by a constant k, and the existence that modulus of del f by del y is bounded implies that f satisfy the ellipsis condition. So, here we stop our lecture. In next lecture we will continue our discussion after this. So, thank you for listening us. Thank you.